and gentlemen, let's talk about evolutionary computation.
Children are true masters at learning new stuff. Give a child a new game and it will immediately start by playing or pressing some random buttons and seeing what happens. You don't have to explain to a child how a game works. And we will rediscover these two properties also in the resulting strategies developed by reinforcement learning algorithms.
So our issues today are quite simply privacy, security, certainly intellectual property rights, but more importantly, diversity, inclusion, harassment, cyberbullying. We have to make sure that we're not contributing to that.
And now you wonder, why though? I mean, what good is it if I can reproduce my input, right? I can do this without a neural network. I just take the input and output it.
So welcome everybody. Welcome to our very next keynote here at the conference. I hope you had great sessions so far, great conversations, and we are approaching the next highlight of the conference. My name is Hartmut. I'm part of the editorial team of that conference, and it's my pleasure to introduce the next keynoter to you. Dr. Neda Navidi will share some insights on her latest research project. I think the pictures show a lot already. It's about the combination of human interaction and machine learning techniques, especially reinforcement learning. Please give a warm hand to Neda Navidi.
Thanks for being here. Thanks for having me here. I'm Neda Navidi. I've done my PhD degree in Quebec University a while ago, and I've done my postdoc degree in McGill University and Polytechnic of Montreal, in mostly focusing on reinforcement learning, different kind of interacting learning, online learning, and something like that, yeah. Now I'm working on a company named Redefined in Montreal, and the team goal is make a combination and collaboration between the human and AI. So I'm really excited to talk about the human and AI interaction training system, in fact. Okay. The things that in our team, we really believe that the human and AI can elevate each other. The vision we have is like as to build a smaller future for improving the synergy between the human and AI. And the last mission we have is providing a universal and safe digital safe place where the human and people can learn from each other. But how is it really working? The thing is that we really believe that through a simulation environment, we can engage the user with the AI agent, and there is kind of two-way interaction. And our unique training model allows the AI agent and the human have the interaction between themselves and also can learn from each other. So if I just want to simplify it, it's like as we create a full loop of continuous learning between the human and AI. Okay, the question is that when the human and AI interaction is useful, there are lots of use cases that is really interesting, but the first one I want to talk about that is when we're thinking about the new skill, learning new skill. Doesn't matter that the learner is the agent or the human, still the other components help that component to learn the new skills. The other use case would be like as when we're thinking about the operating the system by using a group of AI and the human working together. It means that we have a task in the environment. Part of them would be done with the agent, part of them would be done with the human. And I will talk about it later in the live demo in details. And the last one is when we're really thinking about some kind of situation that it's the kind of time-sensitive situation, and we really need the recommendation from the AI, send it back to the human, and the human consider this kind of feedback from agent and consider the decision based on that observation. Now I invite you to look at the video clips. Just examples that how human and AI can work together. If you just take a look at news probably every day, you probably notice some kind of title and topics about that the human trying to replace the AI, or we're trying to AI do the like as the automate the human in different kind of task, in fact. Probably you think that there is kind of replacement for the human, but it's not. But the thing is that we're trying to make the human in the level that understand the ability of the human. We need an agent understand the situation, and the things we're trying to replace it is the human ability, not the human. For example, we have kind of situation that is really hard for human to be part of them, like as a smart manufacturing, a smart discovery, and a smart learning, for example. Who has seen the Matrix here? Oh, cool, cool. So you guys might notice about the following clips.
Can you fly that thing?
Not yet.
Operator.
Tank, I need a pilot program for a B-212 helicopter. Hurry. Let's go.
I know, of course, it's not the real learning process, but it's really fancy. And I really like these clips because it shows that how much, if we use the technology, how much it could be fast, real time. And it's it's really amazing because it's exactly targeted what the user wanna learn, in fact. So it's kind of interesting method of learning. But it's the time to go to the real environment, real world, in fact. When we're talking about the machine learning, mostly we're talking about three different categories. The first one is the supervised learning, and I'm sure that most of you know what's that. We have the data set, we have the label data set, we can use the different kind of model to train the model, and then after we have a model related to that kind of data. The other one is the unsupervised learning, that we have a data set, but we don't have the label data. We can just cluster the data. And the last one is the reinforcement learning. Well, there is no data set here, not at all. So what we can do is like as we're starting from scratch. We're trying to create data set from a starting point, in fact. What's happened here is like as we have an agent, we have an environment. The agent observes the environment, and this observation comes with an action. In fact, the agent takes an action, and environment will send back the reward, positive reward or negative reward or punishment. And with using this kind of reward, the agent can understand about the learning process. Here we have just example. You can see how the reinforcement learning works. We have an agent. We have two options, fire or water. And the thing is that there is kind of the random action that the agent trying to take. It takes the fire. Because of this action it takes, we have as the punishment. It was kind of bad action. So it's understood that it was a bad action. For the next time, they just to prevent do the same action. So this is exactly the process of the reinforcement learning. And no matter what kind of company you're working, I think it's really important to know about the reinforcement learning, because these days the reinforcement learning is useful in different kind of aspects, like as networking, resource management, robotic, and lots of different areas. Besides the reinforcement learning, we have the other concept that names the imitation learning. In imitation learning that we can consider as a supervised learning, there is some kind of coach that the agent observes the coach, in fact, and learn how to deal with the environment. But there is some problem with the imitation learning, and I will explain it later. But before going to the problem it has, I want to make a comparison between the imitation learning and reinforcement learning. When we're considering the reinforcement learning, doesn't matter what kind of reinforcement learning we're using. It could be policy-based, value-based, or model-based, doesn't matter. Still, we have suffer about the data efficiency. Why? Because the reinforcement learning is really hungry for more data, in fact. And also, when we're considering the stability of the system, it's like as the imitation learning work worse, in fact. So it's some kind of, if we're thinking about how we can use these both methods in the same place, we can just tackle the problem we have. So the motivation of this study is that, can agent learn from the human based on the immediate response? And the other question is that, what is the difficulty of human feedback? And how we can integrate the human feedback? So the objective here is like as we're trying to increase the stability and data efficiency of the system by combining two different methods, imitation learning and reinforcement learning. this is our contribution. We propose to have the integrated level of reinforcement learning and imitation learning, and consider this one to improve the sample efficiency and speed of the learning process of the integration system. Okay. We don't have time to go through the different algorithm of reinforcement learning, but if you're really interested, you can go to internet. There are lots of papers related to that. But I want to talk about how we really can put the human in the loop of reinforcement learning. There is an example here. We have a student, and the thing is that we have the agent. The agent we can consider like as a computer, for example, send a math exercise to the student, and the student will send back their answers. And because of the indicator we have, we can see that it's kind of the passing the exam or not. And in that case, the policy is the mapping of the past interaction toward the next activity, and the goal is choosing the maximum student outcome, in fact. I want to change the scenario. Instead of a student, we have a patient, and the agent sends the medication dosage suggestion to the patient, and in the other hand, the patient will take the blood pressure. And because of the indicator we have, we can consider that is it really high or it's really low. So the policy here is different, and at the same time, the goal is choosing the action to maximize the wellness. So if we want to generalize it, it's like as we have the human and an agent. It's take an action by observing the agent action, and because of the reward as an indicator, we can have the policy and goal. So my point is that before going to any kind of environment, it's really important to define a goal of the system, define the reward of the system. We really should know that how it's really working. Okay. Sorry, wait a moment. Okay. Okay. When we're considering for example, a game like as Pong, and we're considering the common machine learning method that is the supervised learning, what we can help the agent to understand what's the situation, we can ask the coach to do, we can ask the player or gamer, is a professional gamer, to do the task, it means play the game, for like as 3 or 4 hours. Then after we can record the data. And what's the data? The data is like as a frame-by-frame information about the screen. And the label data is the action that the, like as a gamer, can take, in fact. So with having this kind of information, we can have the create a policy. But what's the problem of that? It's a really cool idea, but what's the problem? Okay, the problem is that when we're considering these kind of things, we have 2 problems. The main one is that we have a problem with gathering the data. It's not easy. We gather the data in different kind of situations. Sometimes it's really hard. Sometimes it's time-consuming. And we still need people, or like as we need a human to do the things for us, and the agent will try to mimic that one. The other problem we have here is like as long as the agent, when I'm mimicking the human, just goes to the level of the human, not more than that. It means in the best scenario, still we have the agent in the level of human, not better. It's the place we really need the reinforcement learning. It means we're trying to make an agent even better than the human. Okay, the policy gradient is the main method. Probably heard about that in the reinforcement learning. It's really simple kind of method. It's consider the likelihood of the action and randomly increase it. And based on the action that the agent take and based on the reward during the that actions, it can understand that is a good actions or not. And we can create a model, in fact. And if you just take a look at this part, you can see we can have kind of the history of actions and the result, the reward, final reward. But the problem here is that when we're considering the policy gradient, we really suffer from the problem name is the credit assignment problem. And what's the credit assignment problem? As you can see, for example, in the second to third line, you can see we have the like as episode that most part of them it's the correct, but just the last two action is not correct. But what the policy gradient do is like as just trying to skip that kind of episode. They're trying to just like as decrease the likelihood of this kind of action. It's not good for us. So what we can do to solve this kind of problem, because still there is part of the episode that is really interesting. It's the correct action. Just these two actions is not correct. So we can solve this problem with reward shaping, in fact. And what is the reward shaping? We can see the reward shaping like as breaking down the reward or create the reward function. It means, for example, when we're dealing with a very complicated situation like as the Montezuma revenge, you can see it's really complicated environment for the policy gradient to deal how it's really working. But if we consider like as soon as the agent passed the skeleton, received the 1 positive reward. When it's grabbed the key, received 2 positive rewards. When it goes to the next level, receive the maximum reward. So in that case, the agent can understand how they should dealing with the process of the learning. But the thing is that when we're considering the reward shaping, still we have 2 main problems. The first one is that it's not escapable. It's not scalable, sorry. Why is that? Because we really should know about the environment that is designed. We really should know about the reward function. We should do it manually by ourselves to help the agent understand the situation inside the environment. So it's not escapable and scalable, and you should design it by yourself. The next problem we will have with this kind of method is like as we have the alignment problem. It means you define the reward function in somehow, but it's not designed well. It's trying to maximum the reward, but not doing the action. This is an example you can see here. It's the race, but instead of trying to pass the other like as people in the game, it's just trying to maximize the rewards, in fact. And it's not working well. We don't know what's going on. Yeah. Okay. About the imitation learning, I have a publication about it. You can go and take a look at that. Because of that, I will escape this slide about that. There are lots of different kind of imitation learning that we can use them. Okay. As I explained it before, we have the combination of reinforcement learning and imitation learning. And we can tackle the problem of both systems in the same place. In this figure, you can see that we have different kind of blocks, like as a feedback predictor, supervised policy, feedback weighter, feedback flag, and reinforcement learning policy. I don't want to talk about the detail of them, but the thing is that when we're considering the human feedback, we're really thinking about 2 different kinds of feedback from human. Part of the feedback we have is from the really expert human. It's like as it's part of the action space. And the other one, it's like as we have the like as binary one. Okay, the one use case I want to explain it here. It's the continuous card pool, and as you can see in the result, the card just for person doesn't know about that. The card pool is the environment created by OpenAI for the reinforcement learning. So if you look at the interesting one is the card pool, you can see when we're considering the human, in the loop, and is the hybrid model that it's you can see with the green line and red line. You can see we have the much better result compared to the reinforcement learning standalone. I will pass this one. Okay, now I want to talk about the framework we designed it. The name of this framework is Cognate. What we do in Cognate, it's like as we consider the human and agent is in the same place, and we consider both as an actor, in fact. The thing is that we're considering the reward from whole component. It means the agent can send the feedback to human, and human send the feedback to agent. And when we're considering the reinforcement learning, we're considering the agent. When we're considering the imitation learning, we're dealing with the human. And when we're talking about the hybrid learning by the human agent, we use the integrated reinforcement learning and imitation learning. I invited you to look at these clips. It's explanation what's the Cognate. Oh, seems that I have some issue with the voice.
In a continuous loop. All this starts with the cognate.yaml file. And welcome to this first video covering Cognate fundamentals. Every Cognate project starts with an environment and actors within it. They can be agents or humans. They observe the environment through their observation space and take actions within it, learning from each other in a continuous loop. All this starts with the cognate.yaml file. The primary role of this file is to define the actor classes. Each actor is defined primarily by its action space and its observation space. If multiple actors share both of those spaces, they are said to belong to the same actor class. A deployed Cognate project consists of a cluster of services. They are service applications provided by the Cognate framework itself in yellow here, or implemented by the project itself here in white, either by using the Cognate SDK or directly by implementing its underlying protocols. The environment service is responsible for creating and updating environments for each trial. An agent service handles the observations and actions of an agent belonging to a specific actor's class. There will be one of those for each actor class of a project. The orchestrator is the glue that binds everything together. It's the service that client applications will connect to in order to start and run trials, a central piece that can be considered a live interpreter of the cognate.yaml file. Now, since the orchestrator doesn't handle traffic from web browsers by itself, client applications using the JavaScript API must connect through a proxy. That's Envoy.
Okay. If you're really
That
interested...
concludes our quick intro into Cognate fundamentals. For more information, a tutorial, or detailed documentation, head to cognate.ai.
Okay. Yeah, it's the open source framework. If you're really interested to know that how reinforcement learning and imitation learning work in different kind of simulation area, you can go and use it. And now times for the live demo. The link you can see here is the open source live demo. You can go there and see how it's working. Now I want to present the cooperative environment between human and AI. Okay. The name of this framework is the Flame, and if you're going to this page, you can see that it's the game designed to make the human and agent have a collaboration together. The thing is that we consider the agent as a drones, and the human is the driver, or like is a kind of driver for the helicopter, and they consider the control of the helicopter. You can consider different kind of drone. For example, I want to use two of dump drone, one a smarter drone, and one of the smartest one, and start the game. You can go to the link and you can play the game by yourself, in fact. And we start the game. You can see based on the multi-agent reinforcement learning, the drone trying to navigate through the environment and trying to find the fire on the forest, in fact. We cannot see the fire because of the fog of the environment, but they can reveal them for us. After we can have this kind of, like as red line, we understand that part of the forest is under the fire. So what we can do as a human, we can direct the helicopter, go to the, like as a fire, and turn it off, in fact. Or like as go there, we see that there is the other, like has fire there, and it's trying to turn it off. This is just one example of how human and AI can work together. It's kind of the group of human and agent that working together to accomplish a task. If you're really interested to know about the Cognate or this use case, you can go to the presented link. So finally, about the key features of the Cognate, we can tell that we can use them for the live learning, we can use them for the distributed environment, we can have the reward from the human and agent at the same time. Yeah, this is the last page of my slide, so I don't know if we have time for the question or not, but if not, I will be around. We can talk about it.
Yeah. Thank you very much.
Thank you.
Yeah, perhaps we have time for one or two questions. Are there any questions, comments?
Yeah. Yes. 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 This flame environment is one of the example, but still you can go to the Cognate, is the open source. You can just create your own environment and put the agent and human in the same level, can deal it with that. And in fact, the tutorial of the Cognate, it's really straightforward. Yeah, it's easy. And also we have the other kind of example, like as we create a different kind of OpenAI-Gym environment with the Cognate and see that how much is compatible with working with even the different environment. And we're trying to put the human in the loop, even for different kind of OpenAI system, in fact. Yes.
That works only when I can simulate the environment, or I can extend it to other cases?
Well, the thing is that we're really thinking about the hardware of Cognate, but for now, we're now working on the simulation one. Yeah, we're creating the simulation environment because we really need that the human and AI understand each other. So the best way to tackle the problem for now is the simulation, but if we can do like as the hardware of Cognate, we can do it without the
that you showed, you know already the physics rule of the environment. Sometimes those rules are not clear to us. Can it be used in those cases as well?
Yes. About the flame project that I've shown it's based on the real situation. It means it's part of the project for the Thales, that a company dealing with turning off the fire in Canada. And the rules defined in the environment, it's based on the more similar to the real situation, in fact, yeah, based on the physics laws, yeah.
So I can clearly see the reward system on direct consequences. If it's really burned when it touches the fire, can it also deal with indirect consequences? So for example, it's successful, stomping out a little fire that fatigues the robot itself, and over a long time, the water would have been better consequence, something like this.
Oh.
Technologies for that.
Good question. I didn't consider this in this environment. Yeah, but we can do it, in fact. You can use the reward function as you can want, and you can just send the reward in any kind of way, in fact. The thing is that because we're using the orchestrator, it just takes care of everything. Yeah.
So thank you very much for this wonderful keynote again.
Thank you.
Yes, and we are approaching the end of the conference session.